like when we bring these hybridized atoms together to be a molecule, and how can we draw those 3D sketches? Well, if you ever need to do a 3D sketch, the very first thing you want to do is determine the hybridization of the carbons involved, or any atoms involved, because it's the hybridization that's going to determine the geometry. So let's take a look at this first carbon and count the regions of electron density. There's 1, 2, 3 bonds to hydrogen, and then a 4th bond to carbon. 4 regions of electron density means we have an sp3 hybridized carbon, and this second carbon has the exact same arrangement with 3 bonds to hydrogen, 1 bond to carbon. So if we wanted to draw a sketch, we would start with either one of the carbons. Let's do the carbon on the left and draw it tetrahedrally. That's a little bit of an angle. If we draw it tetrahedrally so that we have about a 109.5 bond angle, we have it attached to a carbon and a hydrogen. And where are the other 2 bonds? Well, to be tetrahedral, we're pointing off in this direction. One is a wedge, one is a dash, and that's what a tetrahedral carbon is going to look like. Then we come to the next carbon. He needs to be tetrahedral as well. We've already drawn one of the bonds in the plane. The second bond to be drawn in the plane can be either up here, 109.5, or down here, 109.5. And those would both be okay. Let's draw it up in this direction. Okay, but if we draw this bond up here, then the dash and the wedge are down in this direction. Okay, and if we take a quick look at a model here, this molecule is called ethane, and ethane then has 2 tetrahedral carbons. These are both CH3s. These lines that lead end at nothing, we just assume are hydrogens. And so what we have is the carbon-carbon bond is drawn in the plane. We have 2 CH bonds that are also drawn in the plane, and then each of them has a hydrogen that's projecting out toward you. We draw as a wedge. These 2 hydrogens are pointing away from you. We draw those as a dash. So this is what our ethane molecule looks like. Okay, but notice that there's more than one 3D sketch we can have for this molecule, because we can rotate around this bond. There's free rotation around this sigma bond, and so we would actually have some additional 3D sketches we can draw. So for example, because we can rotate around here, we can have, let's just say we can have the structure where the first carbon stays the same, but the second carbon has the other hydrogen that's in the plane pointing down here. If this is where you draw the 2 bonds that are in the plane, then the ones that are out and back are pointing up here. So really working with models and really helps you understand what a tetrahedral atom looks like, and it's going to be much, much easier to draw the 3D sketches to make them more realistic. But the goal of your 3D sketch is that it actually has the same shape as what you're seeing. Okay, how about a carbon that has a double bond? This carbon has 1, 2, 3 regions of electron density. So this is an example of an sp2 hybridized carbon. And again, this symmetrical molecule has 2 sp2 hybridized carbons. So to sketch that, we draw a trigonal planar arrangement for the 3 sigma bonds. Hydrogen, hydrogen, carbon are the 3 bonds we have there. And on the second carbon, we also have a trigonal planar that's going to share the same plane as the first one. So all these are about 120-degree bond angles. Okay, and those are all the sigma bonds, all being planar. And now we have to show what this pi bond looks like. How do we get a pi bond? Well, that's by overlapping a set of 2 p orbitals. And remember, every sp2 hybridized atom has a p orbital. It's right here. We can kind of draw it as a wedge and a dash on the first carbon, and then a wedge and a dash on the second carbon. And then one way or another, we want to show some kind of interaction between the top half and the bottom half to represent a pi bond. Remember, the pi molecular orbital had a cloud of electron density above the sigma bond and a cloud of electron density below, so this 3D sketch represents that pretty reasonably. And this is a model of this molecule. This molecule is called ethene, and you can see that if we draw it, one way to draw it is just completely to put all 6 atoms in the plane of the board, and then the p orbitals are going to be right here, perpendicular on the first carbon, and the second carbon, here's our p orbitals, they're going to be overlapping above and below the plane. So we're going to draw that as sticking out and sticking back. Okay, another possibility, though, is to draw this with the p orbital and the pi bond illustrated very cleanly. So p orbital on one, p orbital on the other, connection of the two above and below. So that's a nice looking pi bond. But if our pi bond is what we're showing in the plane of the board, what does that do to our sigma bonds, to our hybrid orbitals? Well, now we've tilted the molecule like this, so you can see now that these two hydrogens are projecting out towards you. We need to draw those as wedges, and two of them are as dashes. Okay, now if you're reviewing this molecule perfectly straight on, these are going to be hiding each other. So what we do is we tilt the molecule just a little bit so that the back hydrogens are up a little, or we could tilt it this way so they're down a little. Those are both okay. But we need to show, let's show the two wedges coming a little bit in a downward direction, but really they're projecting straight out towards you. And then the two hydrogens slightly up, and they're back. So both of those are good ways to draw the trigonal planar sp2 hybridized atoms. And this molecule of ethene. Finally, we could take a look at this last molecule. We have an example here of an sp hybridized, two sp hybridized carbons that are attached. We have, it's sp because we have just a triple bond and a single bond, so just two regions of electron density. And so if it's sp, that means we have 180 degrees linear bonds, linear sigma bonds going straight out 180 degrees in either direction. And now we need to represent two sets of pi bonds, which are really two sets of p orbitals. So we're going to draw that. One of them can be in the plane perpendicular to the sp. There's one pi bond. And where is the second pi bond going to be? That's going to arise from the pz orbital on one carbon, front and back, overlapping with the pz orbital, front and back on the second carbon. And again, without making a huge mess, we can maybe show the interaction of this top and back. And what we have actually is actually like a cylindrical type of a structure with this. Here's a model of this acetylene unit. This molecule is called acetylene. This one piece represents the carbon-carbon triple bond. Here's it one carbon and the other carbon, and we have the two pi bonds here. So really what we end up with is actually a cloud of electrons just completely surrounding this linear arrangement. And then we have an sp hybrid orbital sticking out directly in one direction and one in the opposite direction.